Hi, in this video we start the implementation of the AVL balance tree. So let's get started. I'm going to create a package for with the name of AVL because we are going to implement the AVL tree. We are going to have a node and we are going to have a class balance tree. It's going to be the AVL tree itself, and I'm going to create a class from which we are going to test it. So let me start with the class node. I'm going to create a class. I'm going to define a constructor, and in the constructor we are going to get a data and a parent node, a reference to a parent node. We are going to have a self.data is equals to data, self.parent node is equal to parent node. We are going to have a reference to a right child, and at the beginning it's going to be none. We are going to have a reference to the left child. It's going to be none too. And we are going to have a balance number. It's going to be 0. We are going to have a insert method. We will insert data, and we are going to have a helper parent node. And we just have to decide whether the if that data is less than the self.data. It means that we have to go to the left. So we have to check whether the left child is not none, it's not a null pointer, and if it's a null pointer, then we have to instantiate it with data and parent node. Else we know that it's not null, so we have to call the insert method, the data with parent, on the left child. Else we if not self.right child, it means that it is a none, so we have to instantiate it. We are going to create a node with the parent node, and else we just have to call this method recursively on the right child, insert parent node. But on each insertion we have to return the parent node, because we have to check the balance number. If it's greater than 1 or less than -1, we have to make rotations. But here it is just this. So we will have a traverse in order. It's going to be the same as before. So we just have to if self.left child is not a null, we can call this traverse in order recursively. Here we just have to print out the number, for example, or the self.data. And if self.right child is not a null, then we call the right child that traverse in order. So it's going to get the numerical ordering or the alphabetical ordering depending on whether there are integers or numbers or strings, whatever. I'm going to have a method getMin and getMax. GetMax, it's going to be the same as before. I'm not going anyways. if the self that left child, if not that self that left child, I mean right child, because the great elements are on the right child, so not the right child, we just have to return self.data, and else we just have to return self.rightChild.getMax. Okay, def getMin, in order to get a minimum value in our balanced binary search tree. So if not self.leftChild, return self.data, and else we just have to return self.leftChild.getMin. Okay. And we will going to have a okay. I think we will have that's all we have in this node class, I think, or not. Maybe we are going to return to this class the balance tree. We are going to have a, let me first we create a balance tree class with the object. We are going to have a constructor, and in the constructor we are going to define a root node. It's going to represent the root of our binary search tree, and we initialize it as none. We are going to have an insert method. It's going to have a data which we want to insert. So we are going to define a parent node which is equal to the root node in the beginning, and if the self, that root node, is equal to none, then the parent node is equal to node. It means that the binary search tree is empty, so we have to insert at the root. It's going to be a data and none, because the parent of the root is a none, and self.root node is equal to parent node, I think, and else we know that parent node is equal to, we know that we have to insert in the root because it's not null, so it's going to have the self.root node dot, we call the insert method in the node class with which we have implemented so far, insert data self.root node, and we just have to rebalance the tree. We are going to implement this method parent node. Okay, and we have to import, of course, from AVL.node we import the node. Yeah, so we have to define the rebalance tree, and it's going to have a parent node. First of all, we have to self set balance. It is a recursive formula, as we have discussed in the theoretical video. We are going to set the balance of the rebalance tree, I mean the parent node. So I think let me implement that two method. So far we have discussed, yeah, so I'm going to have a set balance method. It's going to get a node, and we just set the node that balance is equal to the self.height of, it's going to be a method, we are going to implement it, node dot right child, and we have to subtract the self dot height dot the node dot left child. Okay, and I'm going to define the def height. It's going to get the node, and if the node is equal to none, then we return -1, else we have to return 1 plus the maximum, as we have discussed, self.height node left child, and self.height node.right child. Okay, it is a recursive formula. We keep iterating it until we get the height, and from the height we can get the balance. In the next video we are going to continue AVL tree. Thanks for watching.